Hello and welcome again to my Physical Science Online Video Lecture Supplement series. Today's video is another post-quiz review, and this is for the lecture quiz number 4. So that would be the quiz that covers work and energy, and by extension power. So let's pull up the quiz results and see how we did. Alright, this quiz seems to have been not as good as the last quiz. So it looks like the average score was only a 52. This semester seems to be a very Jekyll and Hyde semester, shall we say. I've been noticing that every other week you guys are doing pretty well on the quizzes, and every other week the quiz scores are kind of bad. So I guess this was a bad week. In any case, it looks like, according to Blackboard's analytics, there were 3 hard questions, 14 medium questions, 1 easy question. So it says there were 17 completed attempts, so the ones that are maybe of most interest are the ones that 17 people actually attempted to do. It looks like there are 3 questions that we got less than a 40% as a class of the possible points on, and then there were a few random other ones that were the randomly assigned questions that people didn't do so well on. So let's take a look at a couple of these examples then. A couple of these quiz questions. Okay, the first question that I want to look at is the applying your knowledge question number 2 that was on the exam. Of course, it was slightly modified from the textbook. In fact, all of the applying your knowledge questions I have to modify slightly from the textbook in order to use on the Blackboard exam because of the way that those are worded versus how I can actually word an exam that Blackboard will grade. So this one was changed into a multiple choice exam, and then I had one little modification, which is that I asked what happens if there is air resistance and what happens if there is no air resistance. So the question is written right here. You have 2 identical stones that are being thrown from the top of a building. Both of them are initially being thrown with air resistance, and then we repeat, this time maybe without air resistance, and in both cases stone number 1 is thrown straight up and stone number 2 is thrown straight down, and they both have the same initial speed. And so the question is, which of the following are true? So possibility number 1, without air resistance, stone 1 will hit the ground with a faster speed than stone 2. Possibility 2, without air resistance, stone 1 will hit the ground with a slower speed than stone 2, and number 3 is that without air resistance they will both hit the ground with the same speed. Okay, so can we distinguish between those 3 possibilities, the 3 possibilities without air resistance? Well, if there is no air resistance, then it follows that the mechanical energy of the system is conserved. What this means is that for both stones, the potential energy, we will use a PE, so I don't have to write potential energy each time, plus the kinetic energy. Kinetic energy, we can use a KE. These 2 things, when added together, are constant. So that means that this total quantity of potential plus kinetic energy is not changing. So potential energy in this case, PE, for either stone is the mass of the stone times the free fall acceleration, which is what we usually use, a g, times the height above the ground. So height above ground. So we might write this as PE equals mgh. The kinetic energy, on the other hand, is given by the equation 1/2 times the mass times the speed of the stone squared. So that's speed times speed. So this is sometimes 1/2 mv squared. Okay, so how does this let us answer the question? Well, both stones are thrown from the same initial height. Both stones are hitting the ground. So that means that both stones initially have the same potential energy and finally have the same potential energy. So that means that the change in kinetic energy for the first stone and the change in the kinetic energy for the second stone has to be the same. And in fact, since they're both losing potential energy, it means that we're having to give them both the same amount of kinetic energy. Well, the only way for that to have happened is for them to both, since they both have the same mass, it is for them to both have the same speed when they hit the ground. So in order for this energy to be conserved, we need for the final speed of stone 1 and the final speed of stone 2 to be equal. By the way, I started by saying that since they both have the same mass, this occurs. In this case, that's not necessarily needed information. In other words, if we ignore the mass of the two stones with no air resistance, we'll find that they still hit the ground with the same speed upon hitting the ground. So we basically can do that by saying PE initial plus KE initial has to be PE final plus KE final. So potential energy, kinetic energy. PE final relies upon the final height above the ground. Well, when it hits the ground, that height is 0. So this right here is basically saying that the final kinetic energy is the initial kinetic energy plus the potential energy. We can write that in terms of speeds and masses and heights and so on like this. mgh initial plus 1/2 mv initial squared is equal to 1/2 mv final squared. Since there's an m in every one of these terms, if I divide everything in this equation by m, I have the same equation that I had before. So in other words, I'm allowed to do that. It's like dividing every term in this equation by the same number, 2 for example. So 2gh plus vi squared is going to be equal to vf squared, or half gh plus a quarter vi squared plus a quarter is equal to a quarter of vf squared. So I'm allowed to divide by some number as long as I divide everything by the same number. That's just algebra, basic algebra. Okay, so this one right here is showing that the final speed is dependent only on the initial speed and the height initially above the ground, and the local free fall acceleration, which we know g is 9.8 meters per second squared, and that you can review chapter 2 of your text for. Okay, so this all has been with no air resistance. What happens if we add air resistance? Well, air resistance is like a force. It can be treated in some ways to be like friction, if you want. And what that means is that it does work. And as you know, work is force times distance. So the longer distance that a stone travels for, the more work that's going to be done against that stone's motion. So which stone is going to have a greater distance that it travels? Well, in one case, you have thrown the stone up off the top of the building and then it goes down and hits the ground. In the other case, you threw the stone straight down off the top of the building and it hits the ground. This one, you can see, travels farther than this one, which means that more work has been done on this one. So, more work. What is the work doing in this case? Well, it's basically stealing from the energy total. So the way that we would modify this equation is basically potential energy plus kinetic energy is equal to the final potential plus the final kinetic plus the work done. And so again, if this guy goes to 0, if we rearrange this equation by subtracting work from both sides, you can see that this right here minus work is going to be smaller than just this right here. And what that means is that the kinetic energy finally is going to be smaller than it was before, and it's going to be smaller by the amount of work that's done. So the more work that gets done, the smaller the final kinetic energy is going to be. So this one that we did more work on should have a smaller final kinetic energy than this one that we did less work on. So let's scroll through the answers, and what we see is with air resistance, stone 1 hits the ground with a slower speed than stone 2 hits the ground. And that would correspond to the stone that is thrown up being slower than the stone that's thrown down, and that's what we predicted from that little energy analysis. Alright, the next one that I'm going to do for you is this odd-numbered exercise problem. So if you look this up in your book, you'll see that the answer given for this exact problem was 720 joules. So how did they get 720 joules? What they did was they said 40% of the total force is directed downward, and so therefore 60% is directed horizontally, and therefore we have work is force 200 newtons times the 60% times distance. So you'd have 200 newtons times 6 meters times 60%. Now 60% is the same as 0.6. So 200 times 0.6 is 120 times another 6 is 720. With that said, this is one of those kind of odd questions that they ask, because if you dig a little deeper into this question, and I checked what people's answers were with this question to see if they had, trouble with it because they were actually thinking, as it turns out, correctly about this question. Here's what you will see. If I do some amount of work, if I apply a certain amount of force F onto an object, then F can actually be broken up into two components. This is Fy, and this one right here is Fx. Alright, well, X and Y are always at 90 degrees with respect to each other, and it was said that this one right here, Fy, is equal to 0.4 newtons. That's the same thing as saying, it's 0.4 times F. That's the same thing as saying that it's 40% of F. Well, the Pythagorean Theorem says that for a right triangle, F squared should be equal to Fx squared plus Fy squared. So what that means is that Fx squared should be F squared minus Fy squared. Or in other words, Fx is the square root of f squared minus fy squared. This right here you should have learned at some point in your high school math classes is called the Pythagorean theorem. So Pythagorean theorem. Okay, well, we have that fy is 0.4 times f. So that means that we have square root of f squared minus 0.4 f, quantity squared. And so we can pull out a calculator. One thing that you can do here is notice that there's an f here and there's an f here. So you can actually pull out the f squared. So you have f squared times 1 minus 0.4 quantity squared. And so basically we can calculate what this quantity is and then take the square root, and the f squared we can actually now pull out because this is the same thing as square root of f squared times square root of 1 minus 0.4 squared. That's, again, basic algebra. So this right here is equal to f. So let's pull open the calculator and see what this difference of squares, as it turns out, really gives us. So 1 minus 0.4, but I have to square the 0.4 before taking away from the 1, gives me 0.84. And if I take a square root, I actually get 0.916. So what this means is that fx should really have been 0.92 times f. So therefore F, recall, is given as 200 newtons. That means Fy is 0.4 times 200 newtons, is actually 80 newtons. And Fx is actually going to be 0.91 times 200 newtons. So what that should give us is about 183 newtons. 183.3, but we'll just keep 3 significant figures. Well, work should have been Fx times x. So this should therefore have been 183 newtons times the x distance that it traveled, which, if you look back in the original problem, was 6 meters. So we have 183 times 6.0 meters. Therefore, the amount of work done should in fact be 1099.8. So we'll just call that 1100 newtons. So that is the actual amount of work that is done in this problem. The way that your textbook is approaching it is as follows. I'm going to go ahead and move all this stuff up. Your textbook is saying, well, since Fy equals 40% of f, therefore Fx must be the other 60% of f. Therefore, Fx is 0.6 times 200 newtons, which if you put into your calculator gives you 120 newtons. Therefore, the work done is Fx times x, which is 720 newtons. Now, since your textbook basically got this wrong for you, I was lenient enough in grading these that I said, okay, if you put 720 newtons, fine. That will be counted as correct because that's what your textbook told you to do. If you thought a little more deeply about it and got 1100 newtons instead of the textbook answer, even better. because that actually is the correct answer, not 720 newtons. And therefore you should get credit for doing it this way instead. All right, the last question that gave a lot of trouble to people that everybody attempted was this question about a 1 kilogram rock being dropped with zero initial speed from a height of 6 meters. And if there's no air resistance, when is the kinetic energy twice the potential energy? And so the answer should be in meters. You can see the answer here is 2. By the way, the mass of the rock in this case doesn't actually matter. We can solve it symbolically without the mass, but the mass is there in case you want to plug all numbers in, if that makes you a little more comfortable than doing symbolically. Let's see how we work out this problem. Basically what we're doing here is we're using energy conservation. So energy conservation basically says that the initial potential energy, and I'm again going to use PE for potential energy and a subscript I for initial, plus kinetic energy, and again I'm going to use a KE for kinetic energy and a subscript I for initial, should be equal to the final of potential energy and the final of kinetic energy. So I'm using F for final. Okay, so the question here is, at what height, we'll call it H final, is the kinetic energy twice the potential energy? So this is how that is expressed as an equation. Okay. Now it is being dropped with zero speed, v equals 0 meters per second, implies that the initial kinetic energy is equal to 0. So what all of this is saying is that the potential energy initially should be the potential energy finally plus the kinetic energy finally. And using this equation right here, we can plug in to this term right here that this term is equal to twice this term. So we have potential energy initial is potential energy final plus 2 more potential energy final. And so that, of course, you have 1 plus 2, that's 3 potential energy finals. Okay. Now recall that potential energy is given by mass m, so mass times free fall acceleration g, free fall acceleration, times height above the ground. So again, we can write this as mgh. What does this mean for us? Well, as I move this stuff up out of my way, what this means for us is as follows. We can put in that the mass times the free fall acceleration times the initial height is equal to 3 times the mass times the free fall acceleration times the final height. So I'm going to go ahead and divide everything in this equation by an mg. So what I'm left with is that the initial height is 3 times the final height. So in other words, if 3 times the final height is equal to the initial height, that also means that the final height is equal to, we can divide both sides here by 3. It's equal to 1/3 of the initial height. So that's 1/3 of, if we pull up the problem again to remind ourselves what the initial height was, you see that it's being dropped from a height of 6 meters. So the initial height right here is actually 6.0 meters. And so 6 divided by 3 gives us 2.0 meters. So when we're at a height of 2.0 meters, the kinetic energy will in fact be twice the potential energy. Notice, by the way, that having solved out all of this, we can relatively quickly solve for additional questions like at what height is the potential energy, let's say, 5 times the kinetic energy, or excuse me, what height is the kinetic energy 5 times the potential energy? Either way. How would we do that quickly? Well, remember that the equation that was up here that was circled basically said kinetic energy final was equal to 2 times the potential energy final. Let's say that I wanted to solve for the kinetic energy final being 5 times the potential energy final. Well, then I would replace this 2 with a 5, and that means I would replace this 2 with a 5, and that means I would replace this 3 with a 6. So coming down here, if you follow through all these lines of equation, basically this becomes a 6, this becomes a 6, therefore we have to divide both sides by 6, and so you end up with 1/6 of the height initial, and so you'd end up with 1.0 meter instead of 2.0 meters, and so on. You can do this for any ratio you want. Anytime you say kinetic energy is whatever, 10 times the potential energy, replace the 2 with a 10, therefore this 3 gets replaced with an 11, and so you have 1/11th, and so on. Well, I think that's enough for today. So I hope that you found this video helpful. And thanks for watching. Good luck on the next quiz.